bicyclic monoid. So first I start with some sorry, I have a problem. Just a moment. And now. So my report is about partial transformation, partial bijective transformation of some ordered or magic spaces, and about technique which we use it, which close nearly bicyclic monoid. So. As a definition, if we have any non-empty cardinal and partial map from a subset domain alpha from range alpha, so subset from some subset G, which we call the domain alpha to the image of range, we shall assert maps called partial map from cardinal lambda to cardinal lambda, and the domain we shall denote by the alpha and range alpha. So if we have that our map is empty map, we is denoted by empty map, and we state that the domain of empty amp and range empty map is empty set. So if we have two partial map alpha and beta from cardinal lambda to cardinal lambda, the composition of such map is determined the following way. We consider the intersection of the range alpha and domain alpha, and the domain of the composition alpha and beta will be the full pre-image of such intersection, and the domain will be the image under the beta such intersection. So, and by I lambda, we denote the set of partial bijective transformation of lambda together with following semigroup operation. This semigroup I lambda is called the symmetric inverse monoid over the cardinal lambda. Such semigroup was introduced by Victor Wagner in 1950, and uses this terminology. Wagner and independently Alfred Clifford introduces the conception of inverse semigroup. What is the inverse semigroup? Inverse semigroup is a semigroup such that for any x from S there exists unique y such that the following two conditions holds. So if we have, so this element y is called the inverse of x, and it will be denoted as in group theory x is the power minus 1. So this map which possesses any x is inverse is called inverse. So, and Wagner proves the following nice theorem, so that I lambda is inverse semigroup for any cardinal, sorry, any cardinal lambda here is misprinted. Lambda, moreover, every inverse semigroup is a morphic embed into IS by the following map with when we any S put right shift row S. With the following domain is the following range, yeah. We introduce the following subsemigroup of symmetric inverse semigroup, the semigroup of injective partial self-maps of cardinal lambda with a cofinite domains and range. And it is obvious that this semigroup is inverse submonoid of symmetric inverse monoid over symmetric inverse monoid, and we shall call this monoid the monoid of the injective partial cofinite submaps of lambda. Next, very nice definition. Evgeny Sergeyevich Lapin in 1946 introduces the following semigroup: the bicycle monoid or bicycle semigroup. The bicycle semigroup is a semigroup with identity. We generated two elements P and Q, and the subject only one condition: P multiply Q is equal 1. All elements of that semigroup we may write as such infinite table. And why I shall speak about around the bicycle monoid, because all result of my PhD student and my colleagues lies in the methods of bicyclic semigroup. So the bicyclic semigroup has a very, very nice representation. If you consider the following shift alpha, shift on one element of the set of positive numbers, and its inverse partial map beta, then the bicycle semigroup is isomorphic. The semigroup is generated by alpha and beta. And hence we get that the bicycle monoid is inverse sub monoid of the semigroup of injected cofinite partial projection of kernel lambda for any infinite kernel lambda. So it's very well known green relation of for any semigroup. So two elements are equivalent if and only if they right principal ideal coincide. L equivalent left for G equivalent if two-sided ideal principal ideal this element coincide, and the relation D is the relation with its composition L and R, which are commuters, and the relation H is the intersection of L and R. So it's very, very simple exercise that if a semigroup contains exactly one H class, then is a group, contains only R class is right simple, corresponding L class left simple, contains G class is simple, and contains exactly one D class, then as called P simple. So every B simple semigroup is simple. So and the relation between this relation shows the following diagram. And when we have any inverse subsemigroup of symmetric inverse monoid I lambda, then all not all, but R, L, and H relation are described in the following way. And so is the definition of congruence is well known, and the congruence from the semigroup is called non-trivial if this congruence is distant from universal and identity congruence, and a group congruence if the quotient semigroup by this congruence in the group. So every inverse semigroup admits a minimum group congruence or least group congruence in the following way. Two elements are in this congruence if and only if they exist in idempotent E from S such that the following equation holds. So we have that in bicycle semigroup is a subsemigroup of cofinite projection of lambda, and what are property of the bicycle semigroup? All IH classes are singleton, L classes are exactly columns, R classes are exactly row. The bicycle semigroup is simple, hence is simple, and every non-identity congruence is a group congruence. Moreover, any non-isomorphic homomorphic and isomorphic image of the bicycle semigroup is isomorphic to the cyclic group. So what we have in the case of the cofinite partial projection of cardinal lambda. Every maximal subgroup of the semigroup is isomorphic to the group of all projection of cardinal lambda. This semigroup is a simple inverse semigroup, and hence is simple. And also every non-identity congruence on this semigroup is a group congruence, and moreover, any non-isomorphic image is isomorphic to the homomorphic image of the following group, where S lambda is a group of all projection of lambda, and S lambda infinity is a group is a subgroup of S lambda, which consists of elements which has finite support. This is a group which permutate only finitely many elements of cardinal lambda. This image is isomorphic for this semi-direct product. What we have common property? So for bicycle semigroup, where every non-isomorphic homomorphic image extend from usual natural congruence, group congruence from additive group of integer, and there exists homomorphism each with head, so that the diagram is computed similar we get for the semigroup of cofinite projection of kernel lambda. What we have when we consider the set of positive integer, and we consider the only monotone and not decreasing injective partial transformation of n, so that the main is the complement of domain, in complement of range are finite for any element of that set. We consider we get a semigroup such, and this semigroup have similar property as the bicyclic monoid. All H classes this semigroup are singleton. This semigroup is bisimple inverse semigroup, and every non-identity congruence is a group congruence. Moreover, any non-isomorphic image of this semigroup is isomorphic to the cyclic group. We have similar diagram. Every homomorphism is not isomorphism extend to homomorphism of the group, additive group of integer, so that the diagram is commutative, where P sigma is the natural homomorphism which is generated on this semigroup by the minimum group congruence. So we extend this semigroup by the following way. A partial map is called almost monotone if there exists a finite subset A of n, such that the restriction, such restriction is a monotone partial map. By such symbols, we denote the semigroup of monotone almost decreasing injective partial transformation of the set of positive integers. So the set complement of domain and the range are finite for all elements of such set. There exists a diagram which shows that isomorphic embedding this the bicycle semigroup is the inverse semigroup of monotone partial cofinite projection. This is here as inverse, and this is here. What we have property of such semigroup. Every maximal subgroup of this red semigroup is isomorphic to the symmetric group with finite support of omega. This semigroup is a simple inverse semigroup, and every identity congruence was non-identity congruence with this semigroup is a group congruence, and moreover, non-isomorphic image with this semigroup is isomorphic to the cyclic group. We have similar as we get for the previous subset inverse semigroup and a bicyclic semigroup. Next, it is obvious that we make any partial cofinite monotone or almost monotone bijection with we make extend to the set of all integer from the set of positive integer. And we introduce the following two semigroup. So the same semigroup of only for the set of all integer. And we always that we have such inverse inclusion as in inverse semigroups. Yeah. What are the property of this red and blue semigroup? So red is monotone and blue is Helmholtz monotone. First of all, every maximal subgroup of red semigroup is isomorphic to the group of additive group of integer. Every maximal subgroup of blue semigroup is isomorphic to the semi-direct product, where as entity Z is all permutation of Z with finite support for some semi-direct product. Also, these two semigroup are B-simple semigroup, and every non-identity congruence is a group congruence. More than where every non-isomorphic homomorphic image of such to every of such semigroup are a homomorphic image of the direct square of the additive group of integer. So what will be if we consider more largest linearly ordered set? For example, if we consider the lexicographic product of finite chain and the set of all integer, we have many difficult other results, and the last statement does not hold. This result was published by Inna Poznikova and me, and so the description of all congruences is very, very difficult. So, and so these two diagrams describe non-homomorphic non-isomorphic homomorphism of these two semigroup are similar, which are similar as a bicycle monoid. And what will be when we consider more small semigroup? What is a small, more small? We consider the monoid of partial cofinite isometries of the set of positive integer with the usual matrix. So this result was obtained more than 2 or 3 years. All the result with my PhD student, from former PhD student of Professor Komarnitsky, Anatoly Savchuk. And the first, which we remarked that all such cofinite isometries of the set of positive integer have the following property. Such isometry is a partial cofinite shift of the set of positive integers. And hence we guess that this monoid is a submonoid of the set of all monotone cofinite bijection of the set of positive integer. We get the following result. All H classes, this semigroup are singleton. This semigroup is simple, but is not B-simple inverse semigroup. But this semigroup has many non-group homomorphic images. Moreover, this semigroup contains many homomorphic retracts. What is a homomorphic retract? If you have dimorphism from a semigroup S to semigroup S, and if this endomorphism is a retraction, then the image under this homomorphism, our semigroup is called a homomorphic tract. First of all, we proved that this the semigroup Cn, which is isomorphic to the bicyclic semigroup, is a homomorphic tract. Also, Anatoly Savchuk describes some other homomorphic tracts which contains the semigroup Cn, but we have a problem with the full description of set of homomorphic tracts of this semigroup. This problem is open. What are homomorphic tracts of the semigroup of patient cofinite with matrix of the set of positive integer? So next question will be the following. If we have such a diagram inclusion, yeah, what semigroup in this diagram of inclusion has the following property, that every congruence on semigroup which lies between here and between such semigroup has only root congruence. We introduce the following semigroup. So is such partial monotone bijection, cofinite bijection of the set of positive integers, that the restriction of such bijection on the domain without minimum element of domain is a partial isometry of the set of the positive integer. And we prove the following nice theorem. Let S be an inverse subsemigroup of the set of almost monotone partial cofinite bijection of the set of positive integers, such that S contains this monoid as a submonoid, that every non-identity congruence on S is a group congruence. What are the description of the group minimum group congruence, and what is the quotient semigroup of the this semigroup by the minimum group congruence? We prove the following. If S is inverse subsemigroup of the semigroup of almost monotone partial cofinite bijection of the set of positive integers, such that S contain the monoid Cn as a submonoid, then the quotient semigroup S by the minimum group congruence is isomorphic to the additive group of integer. So if we consider any subsemigroup which lies here, yeah, that the quotient semigroup is isomorphic. So here is isomorphic to the group of integer. Also, if any inverse subsemigroup of this semigroup which contains Cn as submonoid is simple. An inverse subsemigroup of inverse semigroup is called full if the set of idempotent coincides of these two semigroup. And we prove the following theorem. Let S be full inverse submonoid of the submonoid of cofinite monotone bijection of the set of positive integer, which contains the semigroup Cn, then every automorphism of S is an identity map. So here, if S is full inverse submonoid, here that's all. Automorphism of S is trivial, yeah. So similar result was proved to the full monotone or order preserving bijection of the set of positive integer with O N or phi N, where O phi N is sub-semigroup of with of N, where, what is a projection of N which preserved in linear order, and the image has a finite finite complement in N, and was proved by Vadim Doroshenko that the group of automorphisms of such semigroups are trivial. But our result, this result, me and Savchuk, don't use this technique of Doroshenko. We use it only technique of the bicyclic monoid, the idea of the bicyclic monoid. So the next one is the next monoid of special cofinite isometries of the set of integer z with the usual metric was introduced by Oksana Bezushchak in the beginning of this century. So it is obvious that this inverse sub-semigroup of the cofinite partial transformation of any infinite cardinal lambda, and Professor Bezushchak proves that this monoid is finitely generated and it has the exponential growth. Also, Savchuk and me prove the following: this monoid is isomorphic to the semi-direct product of the group of isometries of all isometries of the set of all integers, and the free semi-lattices with unit are the integer. Sorry. So in natural, it's very simple exercise that every cofinite partial isometry of the set of positive integer extend to partial cofinite isometry of the set of all integer. Yeah, it's natural to ask: is it true that this semigroup I n infinity is a sub-semigroup ID infinity? So
I'm sorry, you have 2 minutes.
Thank you. No, we get the following result: the semigroup ID of infinity does not contain the isomorphic copy of the semigroup, and the following we describe all homomorphism from IN infinity to ID infinity, and moreover we get the following: the monoid of IN infinity is not finitely generated. More than every finitely generated inverse semigroup is generated by 3 elements. It is very interesting result. It's very difficult to prove proving that let A be an infinite set of IN infinity generated monoid IN infinity, then there exists no minimal subset which generated in A which generated this monoid. Hence, this monoid does not contain minimal set of generators. Thank you for your attention. Thank you.
Okay.